Hi, everybody. Welcome back to Introductory Physics, day 19. We only have 6 days left together and a lot of ground to cover before the end of this class. So hopefully you guys have been hanging in there with me. And as always, if you have any questions about anything we've talked about so far, feel free to ask in the chat or send me an email if you are not able to attend this class in real time. But today I wanted to do some last examples of conservation of momentum with you guys. These are going to be the more advanced examples. And we started off class today watching this video of an experiment that was done by Physics Girl, who's a personal hero of mine. But anyway, she took a basketball and a bouncy ball and a golf ball, stacked them all on top of each other, and then dropped them. And the result was kind of surprising. So if you've never seen an experiment done like that before, or if you didn't get a chance to hear the video that we watched together, I definitely recommend that you check out this link. It'll take you back to the video. It's only a couple minutes long. So definitely do watch it when you get a chance because it's a really cool experiment that she does. And it's one that you can replicate yourself at home if you have different kinds of balls that you can drop. So basketballs, tennis balls, golf balls, ping pong balls, anything like that will work. So yeah, check it out, do it yourself. This is one time that you can try this at home, so it's pretty cool. But anyway, we're going to do an example problem based on this experiment that she did. And I want you, excuse me, I want you to try to set up this problem yourself because it's very, very similar to the problem that we ended with yesterday. So here's the setup. Assume the basketball on the bottom was 10 kilograms and the golf ball was 1 kilogram. So the golf ball is sitting on top of this larger basketball. The golf ball is traveling downward at 10 meters per second, and the basketball is traveling upward at 10 meters per second. So this is looking right at the moment of collision. The basketball's already hit the ground and is coming back up, colliding with the golf ball. What is the final speed of the basketball and the golf ball after this elastic collision? So since this is an elastic collision, remember momentum and energy are conserved in this type of collision. And there you have the equations for momentum and for kinetic energy. So again, I want you to take a couple of minutes, set up this problem, and try to find those final speeds of both of those objects. Again, it's just like an example that we did yesterday, the very last example that we did yesterday. So take a look at it. If you're on a computer, you can also use the notes that are posted on Canvas to kind of help guide you through that. But I'm going to stop talking now and give you a couple of minutes to think your way through this example. All right, so hopefully you've had some time to at least start thinking about and setting up this problem. It does require multiple steps, so it is kind of a lengthy one. If you remember the example problems from yesterday, then you remember that some of them were kind of lengthy. So let's go through this together and see how you guys are doing. So here is our basketball. Initially, it's traveling upward at 10 meters per second. And our golf ball is initially traveling downward at 10 meters per second. Now, in the video, they were stacked directly on top of each other. But just for the sake of clarity of the drawing, I drew them a little bit separated. But we are talking about the moment when they are colliding and the basketball on bottom is about to propel the golf ball upward. So that's the actual moment that we're referring to in this scenario. So starting off with conservation of momentum, that means that our initial momentum is the same as our total final momentum. And since we have two objects in both cases, before the collision and after the collision, we need to include both of them in both parts of that equation. So today I'm going to use the subscripts I for initial and F for final, partly because there was confusion yesterday when I used 1 and 2 like the book does. but also partly just so that you get used to seeing it written both ways. Some professors prefer 1 and 2 for initial and final. Other professors prefer I and F for initial and final. So this way you have some examples of both. So initially, our total initial momentum is the momentum from the golf ball plus the momentum from the basketball. And then same thing with our final momentum because we have two separate objects after the collision, golf ball plus basketball final. We know momentum is mass times velocity. So mass of our golf ball times initial velocity of our golf ball plus mass of the basketball times initial velocity of the basketball. And then same deal for our final velocities. Now we can plug in some of the things that we know. The mass of the golf ball is 1 kilogram, and its initial velocity is negative 10 meters per second. Negative because it's moving down. The mass of the basketball is 10 kilograms, and the velocity of the basketball is 10 meters per second upward, so positive. The masses don't change after the collision, so they'll stay the same. But we're looking for both of those final velocities. We don't know either one of them. So when we simplify this equation as much as we can, we get 90 equals final golf ball velocity plus final basketball velocity times 10. And that's pretty much as far as we can go for this conservation of momentum approach. We can't simplify that any farther. We're kind of stuck with that for right now. But since this is an elastic collision, that means kinetic energy is also conserved. So our next step is to look at conservation of energy, where our initial total amount of energy is the same as our final total amount of energy. It's the same amount the whole time throughout the problem. So initially, we are dealing with the kinetic energy of the golf ball plus the kinetic energy of the basketball. And same thing at the end, kinetic energy final of the golf ball plus kinetic energy final of the basketball. Now, we are not dealing with gravitational potential energy in this case because we're just going to choose a very convenient coordinate system where our 0 point is right there at like the height of the golf ball, but also we're looking at such a small period of time that this collision is actually happening, where there's not actually a substantial change in height that occurs during this collision. And so the gravitational potential energy, the change in that is not substantial at all. So that's another reason why we can neglect it in this case. We're also neglecting the elastic potential energy from the compression of the basketball and the golf ball because we're going to assume that they are as inflated as they can be, and so that effect would be fairly negligible during the collision as well. So when we remember that our kinetic energy equation is 1/2 mv squared, that means that our initial golf ball kinetic energy is 1/2 mv squared for our initial golf ball state. Same deal for our initial basketball state, and then same deal for the final states as well. But we can see right there that there's a 1/2 in each one of those terms. So we'll get rid of all of those 1/2s just to simplify the math. We can't cross out the masses because it's not the same mass value in each term. So we do have to keep the masses there this time. But when we plug in our numbers, the mass of the golf ball is 1 kilogram. Its initial velocity is negative 10 meters per second. So that will be squared because velocity is squared, etc. We're plugging in all of our numbers. And when we simplify this equation, we get 1,100 equals our golf ball's final velocity squared plus 10 times our basketball's final velocity squared. Okay. Well, at this point, we've kind of gone as far as we can go with energy, and we're still not at our final answer. We are closer, so that's helpful. But here are the things that we know so far. Okay, we know from our momentum approach that 90 equals VGF plus 10 VBF. And then from our energy approach, we know that 1,100 equals VGF squared plus 10 VBF squared. Oh, so many letters. Who knew math had so many letters? Anyway, those are the two things that we know. So 2 equations, 2 unknowns. We got to figure out how to solve for those unknown variables. So one way to go about doing that is to solve that first equation for our velocity of the golf ball. So VGF equals 90 minus 10 VBF. And then once we know that, we can plug that into our second equation. But remember, in that second equation, VGF is squared. So we're going to take that whole term that we just solved for and we'll square it. I'm sorry, there's a typo there. This should be plus 10 VBF squared. My bad. So when we go through that math and square that whole term, this is our result. 1,100 equals 8,100 minus 1,800 VBF plus 100 VBF squared plus 10 VBF squared. So we can simplify that a little bit as well. We'll just divide everything by 10. That'll help us simplify it a little bit. And then we can subtract 110 from both sides, and then combine our 2 VBF squared terms to get this result of 0 equals 700 minus 180 VBF plus 11 VBF squared. So all of those steps are just helping us get this equation as simplified as possible. But we're not done yet because we still don't know what either of our velocities are. So I just put those on this slide in gray so you can see our previous results. But as we saw in example 9 yesterday, we have this quadratic form equation. Right? If we remember, the quadratic form is 0 equals ax squared plus bx plus c. Anytime we see an equation that has that same basic setup, we can use the quadratic equation for that. So in this case, our a value is 11 because that's the one that's with the squared term. Our b value is negative 180. And then our c value is that constant, or 700. So when we do the quadratic equation, looks like this big ugly mess. But this right here, this first chunk, is the quadratic equation. Hopefully something that you've seen before many times in Algebra 1 in school. But we'll just plug in our values for a, b, and c to make it look like this. And then when we actually go through and do all the math, we can simplify it even farther to 180 plus or minus the square root of 1,600 over 22. And again, since we have that plus or minus symbol there, that means we're going to end up with 2 different sets of answers, and we'll have to figure out which one of those sets of answers is actually correct. So when we take the square root of 1,600, we get 40. So our first set of answers is 180 plus 40 divided by 22, which ends up being 10 meters per second. And then when we take 10 meters per second and plug that into our first gray equation, the 90 equals 1, we get a VGF of negative 10 meters per second. So that's our first set of possible answers. Or if we take 180 minus 40 over 22, we get a velocity of 6.36 meters per second. So when we take that and we plug it into the 90 equals equation, we end up with a VGF of 26.4 meters per second. So, I'm sorry. Which one is correct? What do you guys think? Which one is correct? The second one, says Gabriel. Why the second one? Because the golf ball bounces right up, not down. That's true. Yeah, absolutely. We look at the sign of the velocity to tell us about which direction it's going. And we know from the video, if you watched the video, that the golf ball is going to fly way up into the air. So it's going to have a positive final velocity. That's definitely a good sign, a good sign in our answers. True. But if we look at this, the first set of answers, it tells us that the final velocity of the basketball is upward at 10 meters per second, and the final velocity of the golf ball is downward at 10 meters per second. And that's the same as the initial conditions of this situation, right? So this first set of answers is telling us about what would happen if there weren't even any collision to begin with. We saw that same result happen with example number 9 as well. So if we just think about this scenario, we know that they're colliding. We can automatically throw out that first set of answers because they imply that there's no collision. So not only can we look at the sign to help us figure out which one is correct, but we have to also keep in mind the scenario itself to help us figure out which one is correct. So in this case, there are our final velocities. And so you can see that after this collision, the basketball is not moving nearly as fast, right? 10 compared to 6.36. But this golf ball is moving incredibly fast compared to how it was, right? Not only did it totally change direction, but it changed direction and then sped up by 2.5 times the magnitude. So that flies real fast way up there, which is the result that we saw in the video. So go physics girl for doing physics the right way, I guess. Anyway, do we have any questions about this example? How did you guys do? Did you end up getting the right answers? Good job. That's great. And that's okay. If you didn't get the right answer, hopefully you, like in the process of going through this solution, hopefully you saw where you might have made some mistakes. So some common mistakes would be forgetting your negative signs for downward velocity, trying a different approach. Okay, yeah, it did not work. What approach did you try? If it's like easy to explain. Okay, treating the golf ball and basketball as one object. Like on their way down as one object? Or on their way back up as one object? Or just all the time as one object? It is kind of strange to think about because in the video it does, I mean, they are resting on each other, so it does seem like it should make sense that you can treat them as one object initially. But again, we're looking at the moment when the basketball collides with the ground. So the basketball has changed its direction and is bouncing back up, kind of bouncing into the golf ball, and is about to launch it up through, well, just flying into the air. Oh, that's a really interesting point there. You thought they would stick together, but you completely forgot about the video when it would just send it flying, send the golf ball flying. Yeah, so that's a really uh, interesting thing there, I think, because so many times we tend to go into these types of problems with our experiences and preconceived notions about what should happen. But if we're ever not really sure about um, what this collision is going to do, like if they'll stick together at the end or not, um, then I would always recommend that you assume it will be an inelastic collision. Not perfectly inelastic, don't assume that they'll stick together, but assume that they will bounce off each other and some kinetic energy might be lost. That's probably your safest assumption. And then as you do the math, you might find that they end up with the same final velocity. And that would tell you, oh, look, they did stick together at the end. They have the same magnitude of final velocity and in the same direction. So if you get a result like that, then that implies that they did stick together, and that would tell you that you did have a perfectly inelastic collision where they stick together. But the safest assumption is to assume that they don't, and then let the math tell you about what will happen. That's a really good point. I'm glad you made that. I'm glad you made that mistake, because that's a really good thing, a really, really helpful point that I would not have remembered to mention. So thank you for that. Okay. So we're going to do, as I said, some more examples today and some more advanced examples. So in this example, a 1,000 kilogram compact car is traveling north at 15 meters per second when it collides with a 2,000 kilogram truck traveling east at 10 meters per second. All occupants are wearing seatbelts and there are no injuries, but the two vehicles are thoroughly tangled and move away from the impact point as one mass. The insurance adjuster has asked you to find the velocity of the wreckage just after impact. What do you tell her? All right. So in this case, we do have another collision. What type of collision is this one? And how do you know? What type of collision is this one, and how do you know? Perfectly inelastic. We have a vote for perfectly inelastic. Does anybody second that vote? Gabriel, defend yourself. Why do you think it's perfectly inelastic? Because after the collision, they move as one mass. Yes, those are good keywords to pull out of this scenario. Remember, we have three different kinds of collisions. Elastic collisions are when they bounce off completely and kinetic energy is conserved. An inelastic collision is when they bounce off, but they lose some of their kinetic energy due to things like friction or um, heat or other types of energy where um, you can't like turn that back into kinetic energy, sound energy, that sort of thing. Um, and then perfectly inelastic collisions, they stick together and move off as one object after the collision. So since we see here the two vehicles are thoroughly tangled and move away as one mass, that leads us to the conclusion that it is a perfectly inelastic collision, and energy is not conserved in this case. We can only have conservation of momentum and kinetic energy when it is an elastic collision, and this is not. So, bummer, no conservation of energy here. But we can still answer this question. Okay, so here is our picture. The truck is traveling east at 10 meters per second. The car is traveling north at 15 meters per second. And so this would be kind of like not quite like a T-bone example because they're hitting their corners, but they'll hit and then they'll move off in some other direction. And we need to um, find that information for this insurance adjuster. So the good thing is, even though we can't use conservation of energy, we can still use conservation of momentum. Conservation of momentum applies um, in all three types of collisions whenever our external forces are negligible. So in this case, the friction of the tires and the road is pretty small compared to the force of the cars actually hitting each other, which is why it can push it across the road, right? So all of our external forces are pretty negligible compared to this actual impact, so momentum is conserved. But now, since we're dealing with not just a collision in one dimension, we're dealing with collisions in two dimensions. So in our XY plane, we have to think about our X momentum and our Y momentum separately. So we're going to break this problem down into its components, its X component and its Y component, and look at them separately. So starting off, looking at the X component of the initial momentum, initially, we have the car and the truck, and they both have an initial momentum because they're both moving. So that initial momentum in the X direction would be the car's momentum in the X direction plus the truck's momentum in the X direction. And again, momentum is mass times velocity. But the car is not moving in the X direction at all initially. It's moving in the Y direction, just north. So that velocity in the X direction for the car is 0, and that term will totally disappear. And so really we just have the truck's momentum in the X direction to think about. And that is the mass of the truck, 2,000, times the velocity of the truck, 10 meters per second. So our total X momentum initially is 20,000 kilogram meters per second. Same idea in the Y direction. Our total momentum in the Y direction is from the car plus the truck, but the truck is not moving in the Y direction initially, it's moving in the X direction. So that term is going to completely go away. And our momentum in the Y direction is just from the car, so 1,000 kilograms times 15 meters per second is 15,000 kilogram meters per second. So there we have our components for the initial momentum, X and Y components. So I just put them up there again for you for reference. So the magnitude of our total initial momentum, remember whenever we're dealing with vectors, we can find the magnitude of the vector by the Pythagorean theorem. So the square root of our X component squared plus our Y component squared. That's true for forces and velocities and displacements and momentums. Any vector it will work for. So our X component, again, is 20,000. Our Y component is 15,000. So spare those, add them together, take the square root, and we get a total initial momentum of 25,000 kilogram meters per second. The direction, again, we learned this equation when we talked about vectors way back at the beginning of this class. The direction is the inverse tangent of the Y component over the X component, which ends up as a 37-degree angle. Okay, so that's our initial momentum, but we know as well that due to conservation of momentum, the initial momentum is the same value as the final momentum. So we also know that our final momentum should be the mass times the final velocity. That's just how we calculate momentum. So if, according to conservation of momentum, initial momentum equals final momentum, then our final momentum is 25,000 kilogram meters per second. And since they're thoroughly tangled and moving together as one mass, our final mass is 3,000 kilograms, right? 2,000 from the truck plus 1,000 from the car is 3,000 kilograms for our final mass. So now we just need to find our final velocity. So that's 25,000 divided by 3,000, or 8.3 meters per second. And again, the direction is 37 degrees. We found that on the previous slide. Oh. Any questions about this example? I think this is the first one where we've had a collision in 2 dimensions. I think. Do you guys have any questions? It's basically the same general idea as collisions in 1 dimension, except you have to set it up in the x direction and then the y direction separately. And then if you need to, then you can combine them. All right, let's take a look at, I believe, the next example. Yes. Example 12, the Great Shopping Cart Race. 2 students were shopping and noticed the floor had recently been cleaned and was very slippery, essentially frictionless. They decided to race their shopping carts. Student A's cart, with a mass of 12 kilograms, initially moves at 2 meters per second, parallel to the x-axis. It collides with student B's cart, which has a mass of 20 kilograms and an initial velocity of 1.5 meters per second. After the collision, both carts bounce off in different directions. Student A's cart moving at 1 meter per second at a 22-degree angle. Find the final speed and direction of student B's cart. What kind of collision is this, and which student is more likely to win now? Dun, dun, dun. Yes. We'll see. I mean, you can choose who's student A and who is student B, maybe at the end of the example. Anyway, here we go. All right, so here is shopping cart A. It's moving with an initial velocity of 2 meters per second. And it hits shopping cart B, which has a initial velocity of 1.5 meters per second. I mean, really, these 2 carts should be the same size, but since they're different masses, they're different sizes in the picture. Anywho, so initially they're both moving in the same direction with different velocities and different masses. And they do what's called a glancing collision. So instead of hitting it like full on the backside, it hits it at an angle. And so both of these carts are going to end up going off at different angles after this collision. I'm not sure if that's a good strategy for student A to like try to knock student B out of the way. We'll find out. But anyway, this is the final state of our collision, our shopping carts. So at the end, the velocity of cart A is 1 meter per second at an angle of 22 degrees. And we don't know anything about shopping cart B, what the angle is or its velocity. So since we don't know what kind of collision this is, we can't assume that energy is going to be conserved because in 2 out of the 3 cases, it's not conserved. So we're going to approach this from just a conservation of momentum approach because momentum is conserved in all 3 collision cases. And then we'll go back and try conservation of energy and see if that works. If the total energy at the beginning equals the total energy at the end, then energy is conserved and it's an elastic collision. If not, then it will not be an elastic collision. But we'll get there in just a minute. Let's focus on momentum for now. So since our shopping carts are going to fly off at different angles, we need to think about this collision in terms of just 1 dimension at a time. So again, just looking at the x direction first. So conservation of momentum, momentum before equals momentum after. So before, both of our objects are moving, so momentum from A plus momentum of B. And then at the end, both of our objects we're assuming, both of our objects are moving, so momentum A and momentum B. Momentum is mass times velocity, so we plug in that equation, mass times velocity, in for all of our momentums. And we can see there that in our final velocity, in the x direction, we have to start using our trig functions again. Because since this final velocity is off at an angle, and we're only looking at the x direction, that means we just need the x component of our final velocity. So since this is our angle, our x component is adjacent or next to our angle. So we're going to use the cosine of our angle for shopping cart A, and also for shopping cart B, right? Here's our angle. This x direction is adjacent to our angle, so we'll use the cosine of beta as well for shopping cart B. Okay, so we replaced VAFX with just VAF. So if you remember when we talked about SOHCAHTOA, Ka, so the cosine of our angle is the adjacent over the hypotenuse. The hypotenuse of this triangle is the VAF, or 1 meter per second. So VAF, hypotenuse, times the cosine of our angle. Same deal with object B. Whew, all right. So the mass of shopping cart A is 12 kilograms. Its initial velocity in the x direction is 2. And then mass of shopping cart B is 20 kilograms. Initial velocity in the x direction is 1.5. And so we'll plug those 12 and 20 back in for our masses in the final side. Our final A velocity is 1 meter per second. Our angle for A is 22 degrees. We don't know what the final velocity is for B, and we don't know what that final angle is. So we'll just leave them in terms of VBF and beta. So when we simplify that equation, plug those numbers in our calculator, we get 54 equals 11.1 plus 20 VBF cosine beta. We can simplify that even farther to 42.9 equals 20 VBF cosine beta. And then if we divide both sides by 20 to simplify it as far as we possibly can, we get 2.145 equals VBF cosine of beta. And I went ahead and I rearranged that equation for beta, well, cosine of beta, and you'll see why I chose to do that in just a couple of minutes. Okay, any questions so far? Okay, not seeing any questions. Let's keep rolling and see how these cards roll. Okay, anyway, let's look in the y direction now. So same deal in the y direction. We set up our conservation of momentum equations, where total momentum before equals total momentum after. We plug in mass times velocity for momentum. But initially, neither of the shopping carts are moving at all in the y direction. So that whole side of the equation just goes to 0, since neither of the velocities have a component in the y direction. But then when we think about their final velocity, they both have a component, we're assuming. They both have a component in the y direction. And since that y component is the side of the triangle that's opposite our angle, we'll use the sine of our angle in that equation. So mass of A times the final velocity of A times the sine of that angle, plus the mass of cart B times final velocity of B times the sine of its angle beta. Plug in our numbers. Our masses are final velocity for A, which we know, and our alpha angle, which we know. Simplify that. So 0 equals 4.5 plus 20 VBF times the sine of beta. And then once we simplify that as far as it can possibly go, just like we did on the last slide, we get negative 0.225 equals VBF sine of beta. And once again, I'm going to rearrange this equation to solve for our angle sine of beta, which would be negative 0.225 divided by the velocity. So at this point, we have two equations and two unknowns. Right? We have our conservation of momentum x direction equation, conservation of momentum y direction equation. We're looking for the angle beta and for the VBF final velocity. So these are the two equations that we ended up with. Now, here's the part where you're going to want to remember your trig functions. So this is like your trig identities. Maybe you're a little bit rusty in these. If you are rusty in your trig identities, I definitely recommend that you take some time and look back through those, because there are a lot of times, not just in math class, but also in physics and in a lot of the other classes that you'll take, where you'll need to know some of these shortcuts, like sine squared plus cosine squared equals 1. And yeah, it's really difficult if you just don't remember those, or don't know how to apply them. So take a second on your own and like look through your trig identities if you don't remember them. But anyway, one of the trig identities that you should remember, because it's very helpful for situations like this, is the tangent of your angle is the sine over the cosine. Tangent is sine over cosine. Well, we know the sine of our angle beta is negative 0.225 over VBF, and the cosine of beta is 2.145 over VBF. So we can simplify that fraction. There's a divided by VBF on both the top and the bottom, and those will cancel each other out. So we're left with the tangent of beta equals negative 0.225 divided by 2.145. So to find beta, we'll take the inverse tangent of that fraction, and we'll get an angle of negative 6 degrees. So I know that's not technically the correct way to write that, because remember, usually we want to write angles going counterclockwise around from our positive x-axis. So this would be, what, 354 degrees would be another way that you could write this angle. I chose to leave it like this just so you can see that like negative 6 degrees means it's down from our horizontal axis by 6 degrees. So it's moved, shopping cart A has hit shopping cart B downward, well, downward at a 6 degree angle. Okay. But we're still not quite done yet, because that's just the direction of student B's cart. That's not the final velocity. But now that we know beta, we can plug beta in to either of those two equations, cosine of beta or sine of beta, and get our final velocity for cart B. So I plugged it into the cosine equation, just because that was the first one. And when you solve for VBF, you get a velocity of 2.2 meters per second. Okay. Again, that velocity is positive because cart B is still moving to the right. And then that negative angle is what gives us the direction of kind of like our negative y portion of it. Okay, so now we've found our final speed and the direction of student B's cart. Next, we need to know what kind of collision this is. But before I answer that question, do you guys have any questions about what we've done so far in this example? Who knew that racing shopping carts can be so intricate? I did. I knew that. Okay. Well, let's continue. So I just put our final velocity up there so that we remember what it is. because it's not there in the diagram. So really what we want to know when we ask what kind of collision is this, really the question that you should ask yourself is kinetic energy conserved, right? Because if it is conserved, then we're dealing with an elastic collision. If it's not conserved, then we're dealing with some kind of inelastic collision. And we can tell that these shopping carts are not sticking together at the end because cart A has a final velocity of 1 meter per second and cart B has a final velocity of 2.2 meters per second. So they are not sticking together. This is not a perfectly inelastic collision. So we're just really debating now, is it elastic or is it inelastic? So let's take a look at the energy. Again, if the initial kinetic energy equals the final kinetic energy, then it is elastic. So initial kinetic energy is the initial kinetic energy from cart B plus from cart A. Kinetic energy is 1/2 mv squared. So we'll plug in our masses and our initial velocities, and we get a kinetic energy of 46.5 joules. So final kinetic energy, now we're dealing with this bottom picture, right? Again, kinetic energy is 1/2 mv squared. So masses didn't change, but our velocities did. So we'll plug in our final velocities, and we end up with a kinetic energy of 39.0 joules. So since those two values are not equal to each other, this is an inelastic collision. So looking at this example, which student is more likely to win, student A or student B? Student me. Lol. We'll see. I would say that student B is probably more likely to win because student B has a greater final velocity and is still moving more in the direction that they wanted to. And so really all student A did was help student B win, in my opinion, you know, because yeah, student A was moving faster at the beginning before this collision, 2 meters per second compared to 1.5. So, I mean, depending on how far away the starting line was, and that could be a whole different problem. But depending on how far away sorry, not the starting line, the finish line, student A was moving faster. So if the finish line was far enough away, then student A could have won by not colliding, but student A did collide with student B. And that just kind of helped boost student B even more forward. Bad strategy. Don't do it. Okay. Well, I think that's the end of example 12. Any questions about this one? Nope, no questions. All right. Let's continue. So you might be asking at this point, can we solve a 2D elastic collision problem? And yes, you can, but it's really kind of a painful process to do so. And here's why. Right, so when we're dealing with 2D elastic problems, we have conservation of momentum and conservation of energy. So, since we're dealing with 2 dimensions, we're also dealing with an x and y component. So our momentum gets broken down into an x direction and a y direction. And if there's 2 objects that are colliding, then you have 2 terms for each of those. And so you can just see this like exponential, almost exponential growth in number of terms that you have to deal with. And you end up with 3 equations and 3 unknowns, which is definitely solvable. It's just a really like long, tedious, somewhat painful process to do so. So I didn't do any examples like that for the sake of time, because I didn't think we would have time to go through an example problem like that. But it's definitely doable. And here's the approach that you would take if you are confronted with one of these kinds of problems. And it's really very similar to what we just did. You take the x and y momentum conservation equations. So total momentum in the x initial equals total momentum in the x final, and then you set up a same equation like that for y. And if you're dealing with 3 dimensions, God bless your soul, but you would set up that same sort of equation in the z direction as well. And then we would also have a conservation of kinetic energy equation, where total initial kinetic energy equals total final kinetic energy. We split those into a term for each object. So if there are 2 objects, then the total momentum x initial is the x momentum of object 1 initial plus the x momentum of object 2 initial. And you would do that for each equation that you have. So then you'd plug mv in for momentum and 1/2 mv squared in for your energy. So if we're dealing with just 2 objects colliding as an elastic collision in 2 dimensions, like your, I guess pool isn't really a very good example, but let's say you're like rolling 2 pool balls against each other and they hit and they go off in different directions. That would be this kind of collision. But you'd have 3 equations with 12 terms and 28 different variables and numbers to keep track of. You can definitely do it if you're organized, but again, it's just painful. So how many would it be for a 3-dimensional one? Too many. I don't even know. It depends on your particular scenario, if you're dealing with 2 objects versus more than 2. And we'll do an example of more than 2 objects soon. Will you be tasked with that in the spring? I don't know. It depends on how cruel your professor is. You will probably not be tasked with a 3-dimensional elastic collision, but possibly a 2-dimensional elastic collision. That is definitely a valid thing that they could make you do. Yeah, for sure. It's possible. Okay, example 13a. We're going to look at 2 slightly different scenarios for a ballistic pendulum. So this one is 13a. But a ballistic pendulum is basically like a block of wood that's attached to a bar or a string or something, and you shoot, well, in this case, some dude fires a bullet at it and makes it swing up into the air. And we want to know how far up it swings. So some dude fires a bullet with a mass of 0.01 kilograms and a velocity of 450 meters per second into a stationary pendulum made of a block of wood with a mass of 2 kilograms. The block stops the bullet, which is then embedded into the block, and they swing up a certain distance. How far do they swing up? So first of all, what kind of collision is this? And how do you know? Perfectly inelastic. How do you know, Gabriel? What keyword gave you that clue? Embedded, yes, embedded into the pendulum. So they are moving as one object at the end of this. So this is a perfectly inelastic collision. They're sticking together, but they're like within each other. Okay, anyway. Yeah, so this is a perfectly inelastic collision. And I just have said multiple times, you don't use conservation of energy. Kinetic energy is not conserved for a perfectly inelastic collision. But we are going to have to use conservation of energy in this example to figure out how high it goes. So it's kind of a weird thing to think about, but it's not contradictory that I'm saying that. So we're going to approach this problem first using conservation of momentum because we know that to be true. And then after we've figured out our answer for the conservation momentum problem, then we'll take a separate conservation of energy problem. But in this case, we're looking at kinetic energy and gravitational potential energy. You'll see. So step 1, find a new velocity, and step 2, find the final height. Okay, so this is what a ballistic pendulum looks like. And in Physics 1 lab, there is a ballistic pendulum experiment where you will, I mean, not like firing bullets, but you will be firing projectiles into a ballistic pendulum and seeing how high it swings up. So get ready for that. But this is what the setup looks like. So conservation of momentum always applies. Initial momentum equals final momentum. So we're dealing with the bullet, B, and the wood block, W. So the total momentum before the collision equals total momentum after collision. So our mass of the bullet is little m. The velocity of the bullet initially is VIB. The mass of the wood block is capital M, and its initial velocity is VWI. And then we know at the end they are connected to each other. The bullet is embedded. So we're dealing with like one slightly heavier object. Mass of the bullet plus the mass of the wood block as it swings up and it has its final velocity. So when we plug in our numbers, the velocity of the wood block is initially 0 because it's stationary, it's just hanging there. So that term goes away. We get a final velocity of 2.24 meters per second. So that was step 1. Step 2 is actually answering the question, how far do they swing up? Now, there are 2 different approaches that you could use. Sorry, I'll go back. There are 2 different approaches that you could use for conservation, to figure out how high it goes up. You could use conservation of energy, which I think is the simpler way to do it. So that's the way that I'm choosing to do it. But you could also use kinematic equations and projectile motion. I just think that's a little bit more complicated than energy, but it is also a valid approach. Okay. So here's our final velocity that we got from the previous slide. Now I'm going to use the conservation of energy approach to find out the final height. So at this point, we're kind of going to choose a different initial and final state that we're considering for this problem. So at first, when we were thinking about how to find the velocity of the block at the end, the block plus the bullet, our initial state was like the bullet speeding towards the stationary block, and the final state was right at that collision as it's about to swing upward. Now we're going to choose the initial state to be at the point of the collision when it's about to swing upward, and the final state to be when it's swung up as high as it possibly can. So that final velocity that we found in the first part of this problem is actually going to turn into our initial velocity for this second part of the problem when we're trying to figure out how high it goes up. So at first, just like conservation of energy problems that we did last week, we're dealing with kinetic energy of moving things plus gravitational potential energy because it's going to be swinging up a height above that reference point. So our initial total energy is kinetic plus gravitational potential. Our final total energy is kinetic plus gravitational potential. At first, though, there's no gravitational potential energy because the block and the bullet are at that reference point. So the height is 0. And then at the end, there's no kinetic energy of the block because it's as high up as it possibly can go before it starts coming back down. So its velocity up there is momentarily 0. So our initial state is this bullet inside of the block, and its initial velocity is that final velocity that we found for the first part, which I know is very strange. We have a big M plus small m term in both sides, so we're just going to ignore the masses, cancel them out on both sides of the equation. So 1/2 v squared equals gh. When we do the math for that, we find a height of 0.256 meters. Okie dokie. But there is a second part. I know we just have a couple of minutes left. There is a second part to this example, which this is definitely a do not try this at home kind of example. I'm sure you can definitely find like YouTube videos of somebody setting this up in their backyard and like shooting a gun at this wood block from like several inches away. That's a really dumb thing to do. Don't do that. Because what if the bullet ricochets? That's a bad day. And so we're going to look at the case where the bullet does ricochet off this block. We're going to assume that you are standing in such a way where you do not get hurt. Nobody gets hurt from this. But the bullet is going to ricochet off the block instead of being embedded into it. So here's that scenario. The bullet then ricochets off the block at 250 meters per second. The block swings up a certain distance. How far does it swing up? So before we go through this and I show you the differences between this version and the previous version, what do you guys think? Do you think the block is going to swing up farther, not as far, or equally as far as when the bullet is embedded into it? For the sake of time, just make your guess in your head and we'll see, well, you'll see if you are correct. We're going to start this problem the same way. Conservation of momentum. So initial momentum equals final momentum. We're dealing, this time our final momentum is two separate objects. The bullet is separate from the block at the end. And it's ricocheting at 250 meters per second. So that means it's bouncing back towards you at 250 meters per second. So that's a negative velocity that we're plugging in there for the final velocity of the bullet. Okay. So we get a final velocity of just the block then to be 3.5 meters per second. And now when we want to find how far it swings up, again, that final velocity is going to become our initial velocity for our energy part of the problem. So conservation of energy, same setup as before, but now we're dealing with just the mass of the block. We want to know how far the block swings up. So it's just capital M. But since that capital M is on both sides of the equals sign, we can cancel it out and we don't even need the mass at all. So when we plug in our velocity that we just found in this case, we see that it'll swing up to a height of 0.625 meters. So previously it was 0.2 something something, and now it's 0.6 something something. So it's swinging up almost 3 times as high with the bullet not embedded into it, which is kind of surprising, I think. Yeah, it's kind of surprising. But that means like if you happen to be standing on a ledge and your friend is throwing a basketball at you, because I've heard that that's a common thing to do. You know, standing on a ledge with your friend pelting you with basketballs. It would be better for you standing on the ledge to catch the basketball than to let it bounce off of you. Your velocity will be smaller if you catch the ball than if you let it bounce off of you. So note to self, if you're ever in that scenario where you're being pelted by basketballs on a ledge, catch them. Don't let them bounce off of you. And that has been your physics tip of the day. Anyway, yeah. Are there any questions about this example? We are just 2 minutes past our time, and I do still have one more example that I want to do for you guys, along with our end of the chapter conceptual questions. So we'll start off with that last example of an explosion with 3 pieces, 3 objects to consider. We'll start with that tomorrow. We'll do our conceptual end of chapter review, and then we'll move on into some rotational motion stuff tomorrow. But I hope you guys have a great day, and I will see you tomorrow. Bye.